the Flatiron Institute in New York City. Her research interests involve black holes, general relativity, gravitational waves, and computational astrophysics, and she has over a dozen lead author publications in her field. She is passionate about diversity, equity, and inclusion in STEM, and seeks to make this a focal point of her teaching and mentorship at PCC. Please give her a warm welcome.
Hi, everyone. Okay, I'm just going to take my mask off. Thank you so much. Some of my students presented at the poster session, and I walked around, hi Tojan, and saw everyone's fabulous posters, super impressive. So thank you, everybody who made a poster, for sharing your passion for STEM with us. So today's workshop is going to have two parts. One where we're just going to look at some images together, kind of appreciate the role that computation plays in modern day STEM. And then there's an interactive part where we're going to actually do some Python coding together. And all you need to be able to do this is a web browser. So I've cooked up a Python notebook for us. I'm going to have a link and a QR code. The only thing you need to run this is a web browser. You don't need to download Python or anything like that. And I've also seen people do it in my physics lab, like on their phones. So you can be able to do it that way too. But we'll start with just some context, which is that computation is everywhere in modern day STEM. One thing is, if you want to get involved in STEM research, if you want to be competitive, let's say for internships, or graduate school or undergrad, stuff like that, it's very important to hone your computational skills, because centuries ago, most of the problems at the forefront of STEM were tractable with just pencil and paper. But these days we're working on more cutting edge problems that get more complicated, that really require harnessing the power of computation. So I have a few examples here from other research fields. And again, I'm not an expert, for example, in computational aerodynamics. But the idea is that if you have an object, let's say, as complicated as an airplane, these days on airplanes they have very, for example, specific wing tips. Something like a jet has a very specific shape. And these are designed using computational hydrodynamics simulations, where people model the shape of an object, and then they use the equations of fluid dynamics to just model, for example, how airflow over an object would behave. How, for example, how much lift you would get. What sort of turbulence would you be seeing? And really use this to optimize, for example, the shapes of airplanes to make them, let's say, the most fuel efficient. Computational biology, I'm not a biologist, but computational biology has really come a long way, where before, working on something like the human genome was kind of slow going, until all of a sudden there was this revolution in computation where people were able to harness the power of computation to map the Human Genome Project. And you can see this explosion in what we know about the human genome thanks to computational science. Similarly, there's computational biochemistry. Again, I'm not a chemist, but to think about things like protein folding, for example, which is a very big topic in something like drug discovery. So something like, let's say you're wanting to go into pharmaceuticals, wanting to create medicines that could cure certain illnesses. A lot of that is understanding how proteins in the human body behave. And these are actually very complex chemical systems. If you think about kind of the microscopic level, we only have a pencil and paper solution for how a hydrogen atom behaves. That's all we know how to do with pencil and paper and quantum mechanics. And then everything else, to really get a grasp on it, is computational. So if you're, let's say, a biochemist or interested in medicine, there are plenty of applications of computation there. We have a very strong geology program here at PCC. And again, if you really want to model realistic physical systems, so here, for example, uh, is a simulation of, let's say, some sort of seismic activity. For that, what you really need to do is work with computation in order to do things like earthquake prediction. Yes? Oh, okay, hold on. I think, so you can just pick which one you want to unmute. I think we can just click this. Should we just click this?
How about now? Do they?
Is it still muted? How about this? Is that still muted? Okay, does that work? If somebody's monitoring the chat?
Yeah, that doesn't work for.
Okay, so somebody said yes in the chat. Okay, excellent, thank you. Okay, so if you were on the Zoom, the thing that you missed is just me stressing that computation is everywhere in modern day STEM and is vital to modern day STEM research. And then if you're interested in kind of more fun stuff, let's say, if you want to go into something like animation, computation really plays a strong role there. You know, the reason that a company like Disney Pixar is able to produce really realistic looking snow for the movie Frozen, for example, is because they use computational or approximations to computational hydrodynamics to be able to model the snow. And I really like this animation where here what they're doing is they're playing with different physical parameters of the system. And they're just running simulations and seeing which one by eye behaves the most like snow. You know, this isn't physics that we know with pencil and paper. It's really how can we use computation to best approximate a physical system. So hopefully I've convinced you that in a lot of areas of interest, computation is extremely important. And then for my specific research field, what I'm interested in is what's known as numerical relativity. So really solving Einstein's equations or the equations governing the behavior of space-time on the computer, which lets us model some of the most extreme systems in nature, such as merging black holes, supernova explosions, so what a massive star does towards the end of its life, things like jets, things like binary neutron star mergers. If you're interested in any of this, just come take my astronomy class. We talk all about these systems. And this involves, you know, a heavy amount of computation. We actually use supercomputers to be able to do this. We do full numerical evolution where space-time itself, the fabric of space and time, is the primary variable that we're evolving, and we're able to get out predictions for things like gravitational wave detectors that will then be able to observe the physical systems that we're simulating. This isn't really a talk about this type of research, but I'm very fortunate that I have 5 or so research students working with me right now at PCC, so you know, shout out to them. It's an exciting field. And then maybe in popular science, you've seen this movie of like what 2 merging black holes would look like. If you were at the first part of the workshop, you may have passed by the LIGO table that they had there. This is all thanks to a computer simulation on supercomputers of what 2 black holes would look like. So we're going to perform a computational astrophysics simulation together. We're not going to use Einstein's full theory of general relativity. Instead, we're going to use a simpler physical principle, which is just Newtonian gravity, which is the gravity that you learn about when you start, you know, either high school or college level physics. And the general idea is that any 2 objects with mass have a force of gravity between them. There's a force of gravity, you know, between me and this camera right now, but overwhelmingly there's a force of gravity between me and the Earth. And that's the thing that really governs the physical behavior that we have. But the idea is that if I take any 2 objects that have mass, and here I have just modeled two masses. This can be anything that you want to conceive of. This could be a star and a planet. This could be an astronaut and another astronaut floating in space, for example. As long as these two objects have mass, there will be a gravitational force between them. They will feel a gravitational pull towards one another. And in Newtonian gravity, we have a precise way of writing down this force. This isn't, a physics lecture, but the key thing here is that you give me the masses, you give me the mass of this object, the mass of this object, and you give me the distance between them. So for example, the distance between the Earth and the Sun, or the distance between our two astronauts who are floating in space. And I can tell you what the force of gravity is between the two objects. And in physics, what happens is that once you know the forces in a physical system, that allows you to relate them to the motion of the system. So long as I know these masses and this distance, I can compute the force, and then I can say, how are these objects going to behave as a function of time? And I just want to stress that this g here is just a constant. It's just a number. It's universal in nature. And this formalism for describing gravity is a wonderful formalism. I want to say that we call it Newtonian gravity, but really there were people all over the world, including the Islamic world and the Indian subcontinent, like Brahmagupta, Al-Biruni, Ibn Sina, who contributed to this theory of gravity. But the key thing here is that it works very well for most physical systems. So when you do, physics for the first time, you'll do things like model the motion of a projectile. That's due to Newton's force of gravity. If you even want to model, let's say, the Earth going around the sun, this is a wonderful framework to use. To be more precise, you would need general relativity, but this is good enough for us right now. Now, here I just showed an example with two objects, but what if we had three objects in our physical system? And what's interesting is when you have three objects, you actually get very interesting dynamics. A three-body system is primarily unstable, and so you're going to see kind of chaotic behavior in the system. But in order to compute the physics that's going on, right, in order to model this motion, what I need to know are the forces that are at play. And the key thing here is that if I think about the physical forces that are present on this object, force from this object, force from this object, and then I can think about a resulting force that it's going to feel. That's the sum of the two forces. But the key thing here is that to find the force on this one, I need to compute something with this one, and I need to compute the force from this one. Similar deal, if I'm interested in this one, I need the force from this one, and I need the force from this one. So on the whole here, I'm computing 6 forces. If you want to be smart and use Newton's third law, you only need to compute 3 forces. But the key thing is that this gets complicated very fast. So if I had even more objects, let's say, it would quickly become a more complicated calculation, for which, as we'll see, we can use computational physics. The thing is, if I start with some system of a variety of many masses at some time, in order to use the equations of physics to see how it would behave at some later time, right, to calculate the forces, what I need to do in order to do this is I'm going to have to take, let's say, one object. Let me pick this lowest one here. And I need the force from this object, this one, 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 this one. That's already a lot of computations. If I want to do this object, I have to do the same thing. And very quickly you run into a scaling issue where if you try to do this by hand, it becomes very, very hard. Suddenly you're keeping track of 10 objects. For each one of those objects, you're roughly computing 10 forces, or 9 forces, let's say. So instead, what we do is we let the computer calculate the forces. We tell the computer, hey, here are the things that I have in my system, here are my masses, please compute the forces for me, and then relate that to the motion of these objects. And so we get what's known as n-body gravitational physics. N here referring to the fact that we can have n objects in our system. So we showed two-body physics, we showed that three-body problem, and here this is just generalized to any number of masses. So here are just some simulations of what's going to happen if I set up some masses and I just let the force of gravity do its thing. I set up these objects with some initial positions, their masses, some initial velocities, right, a speed and a direction that they're heading in, and then I just let the force of gravity do its thing, and my computation tells me exactly how the system is going to behave. And you might ask, well, okay, this is all well and good, but how does this apply to the real world? Well, something like this can actually model the behavior of some well-known astrophysical systems. So there are things in nature known as globular clusters, which are just kind of clusters of stars. They can have 10,000 to around 10 million member stars. Here is just a zoom in on an actual observation of a globular cluster near us. Here's one of the closest ones. You can see lots and lots of stars here, especially a concentration of stars towards the center. And you get this very interesting n-body type dynamics in the globular cluster because each of these stars is feeling a gravitational force from the other stars. And so you kind of reduce to that problem that we were talking about before. Of course, you also have to think about things like, okay, these are stars, I have stellar astrophysics, but to a leading approximation, something like n-body physics is good enough for this. And the closest globular cluster to us is around 30,000 light years away. To put in context, the Milky Way is around 100,000 light years in diameter, so it's actually not that far from the plane of our galaxy. And it has around 100,000 stars. Here's an image of it. And if we were to live in a globular cluster, here's what our sky would look like at night in terms of the amount of stars that we would be able to see. With the naked eye, you should be able to see around 6,000 stars if you're in the desert, for example. But if we lived in a globular cluster, the sky, would just be lit up with all of these stars. And here's another animation of what things would look like around you if you lived in a globular cluster that I really like. And there are some black holes in globular clusters as well. N-body physics is also used to model the behavior of the early universe. So what happened in the early universe is that after the Big Bang, you came to what's known as the Dark Ages, when you just had a lot of gas around. You basically just had hydrogen gas, and then you had dark matter, which is the primary, one of the primary matter components of the universe. And the idea is that dark matter is just something that feels a gravitational force, and it started clumping up to form what are known as halos that were then the seeds of galaxies. So if I start with some initial configuration of dark matter and I just let the force of gravity do its thing, this is an n-body simulation, what happens then is I start to get these clustering things, and that's exactly what then is going to allow galaxies to form in those regions there. So this is also very important in cosmology, which is the study of the universe. But what we're going to do now is we're actually going to simulate globular clusters with Python in our browser. So here I have a QR code, and then here I have a link. So just tinyurl.com/my last name. It's actually misspelled on the Pi Day poster. So it's OKOUNKOVA, Pi Day. And so that should take you to a page that I'll put the link up in a second, that looks like this. And I'm going to talk us through all of this. We're going to run this together, and you'll have your own globular cluster simulation. So if somebody's on a laptop and wants to go to this link, and then, if you want to use your QR code, please feel free. And the key thing here is that if you want to be able to change the code, you are going to have to just save a copy of it in your Google Drive. So if you want to actually play around with different parameters, and I'll prompt us on how to do this, you're going to need to save a copy in your Google Drive. Otherwise, you can just run mine. Okay, how are we doing? Anybody need more time to pull this up? Anybody lacking success? Okay, are we feeling okay with this? No? Okay, what are you using to do it? Need more time for what? Okay, to get the URL? Okay. Okay, anybody else need more time? Okay, excellent. So in that case, what we're going to do is start ourselves off. So in this notebook, I have divided it into 4 cells, and I'm going to talk about what each of these cells does for us and what it's really doing in the context of computational STEM. So first, I just have a little title for myself. It's always very good to document code, and part of this is adapted from this code by Philip Mox from 2020, but I just kind of adapted it for us to make it easier and to make our animations a little bit prettier. So where it says step 1, it says import the libraries for computation. So what does that mean? So something like Python is a very powerful language in itself, but the beautiful thing about Python is that there are also all of these kind of expansion packs for Python. There are core engineers who work on developing Python as a language, but then there's this wonderful ecosystem of people who develop libraries to do a variety of applications. So for example, there's SciPy, which allows you to do scientific computing like Fourier transforms, for example, curve fitting, nonlinear optimization problems. Something like matplotlib, which we'll be using to actually plot scientific results. If you open any scientific paper these days, most likely the plots were produced using matplotlib. This is kind of the industry standard for producing plots. Something like pandas lets you work with large data sets. Something like NumPy, which we'll be using, really lets you work with arrays. It's very similar in that sense to MATLAB, which has a lot of strengths when it comes to matrix manipulation. Similar thing with NumPy, but really there are so many Python libraries out there that if you have an application that you're interested in, let's say you're interested in like machine learning, for example, there are tons of Python libraries to help you do what you're interested in. And so we can see that in this first cell, what I have done is I have imported matplotlib and NumPy. So I've just imported some stuff from this matplotlib library and then the NumPy library. So basically I'm telling it, oh, I want to do some numerical manipulation with arrays. That might be meaningful to you if you've taken computer science. And then I want to do some pretty plotting with matplotlib. So what we're going to do is just press the play button next to the first cell. And what it says is allocating connecting. This is just because we're running it on the Google Cloud. So right now we should all be connecting to a Google server, and Google's probably like, what are these 100 pings we're getting from Pasadena, California? But here is it confirming that we have run. We see a little green check mark here. And so if I can have people just press play for step 1, and make sure that you have the green check mark. And then when you have a green check mark, just look at me and I'll see eyes. Okay, anybody need more time? Okay, so we haven't done any scientific computation so far. Right now, all we've done is say, hey, I know the power of Python. I have some specific application I want to do. Here are the libraries that I want to use. It's very similar to an expansion pack for something like a video game, for example, or like a Chrome extension. So now, what we have in step 2 is the physics. So here, this is what's known as a function. So functions are very powerful computational tools. They're exactly like what functions are in mathematics, right? A function, you give it some variable, you give it some parameters, it gives you back a result. And that's exactly what this def, this is telling Python, I want to make a function. I gave the function a little name. I told it some parameters. And what I'm saying here is I want to know the accelerations of the system. I want to know how these particles in my system, how these stars are going to behave. And I'm going to tell it their initial positions, their masses, and the gravitational constant. And the wonderful thing there is, again, if I know positions and masses, I can use Newton's law, right? This is just sensitive to positions, so the distance between two objects and the masses, and this Newton's constant here, and that's enough to tell me how the physical system is going to behave. Okay, hold on. Boop, boop, boop. Okay, so step 2 is just something we'll run. All this is doing is saying, hey, I'm going to define a function. I've written some documentation for the function. Literally, it's just on each particle in our globular cluster, let's say each particle is a star. Here is my result for how it's going to behave in time, what the change in its direction and speed is going to be. That's the thing that's going to allow me to get the dynamics. So if we run this function, again, little green check mark if we press the play button, all this is doing is just defining the function. We haven't computed anything yet. We're just saying, hey, when we're ready to do the computation, this is the computation that we'll be doing. We're going to call this function. Okay, did everybody get the green check mark? Okay, excellent. So that's just baking in the physics. If you have a different scientific application you're interested in, you're going to have a different set of functions that you're going to call. I can change the properties of physics. I can change what this function is. But for our particular application where we're interested in the force of gravity, that is baked into this function. And we're not a physics class here, so we're not really going to change the laws of gravity for now. But you have access to it under the hood. If you really want to, you absolutely can. Step 3 is setting up the parameters of your simulation. So right now we're just going to keep them fixed to the parameters that I have. But the general idea is that when you set up a physical simulation, you can set up initial conditions. And these can be different for different physical systems. So in the context of globular clusters, we have lots and lots and lots and lots and lots and lots, so many globular clusters around us. And each one of these is different. Each one of these has a different number of stars in it. Maybe the stars have different masses. Maybe they have different initial positions in terms of where they're located with respect to one another. And so when you do a simulation, one of the things you do is you just set up some initial conditions. So here in step 3, I have just set some values. So n, in this case, refers to the number of particles. Here I'm saying we have 50 stars. That's not very physically realistic, right? We expect 10,000 to 10 million stars in globular clusters. But because I don't want to break the Google server, I'm just going to say I have 50 for now. And then when you're at home, you can try increasing this number and seeing, to what extent your runtime changes. These days, there are much more sophisticated algorithms for how to treat n-body codes. They make a lot of smoothing approximations, stuff like that. But for ours, we're just doing the brute force approach where we're actually computing every force. In this case, this is the total mass of my system. The units here are a little weird. I've set G, the gravitational constant, equal to 1, but if you want to, you can put in the value in terms of kilograms, meters, seconds, and work out a mass of the star in something like kilograms. But here I'm just saying, oh, here's a value for the total mass, right? I up the mass, I expect the gravitational force to increase. Here in this simulation, I've just said that all the objects have the same mass, just to simplify it, but you can absolutely change that. Here's the end time of my simulation. I'm just going to, if you want to run it for a long time, you just change this number. This dt is my time step. What you do is you just compute the forces, advance the system. Compute the forces, advance the system. You keep marching on. This is very similar to animation, right? You don't animate the full thing. You do a cell, a cell, a cell, and then you put those together and you get your, full animation. And this is what we're doing. We're just taking a time interval and we're slicing it up into little pieces. And as we move from piece to piece, that's fundamentally what it means to simulate something. And then here's the value that I've stuck in for Newton's constant, but you can play around with this. That's kind of the beauty of this. You can say, well, what if the gravitational constant were different? How would the dynamics change? And so it's wonderful because not only do we have something that represents the physical world, but then we can put in nonsensical values and see what breaks. So let's run step 3, which again, we should get the green check mark pretty fast. Because this is just defining a lot of variables. In Python, you say, it's kind of like x equals 3 type of deal. I'm saying that n is equal to 50. When you see n in the computation, just put the number 50 in there. Okay, how are we doing on step 3? Okay, excellent. Okay, so here's the last step, which is actually running the simulation. So it's going to take our initial conditions from step 3, what we've set up our physical system to be, and this is going to run our simulation. So the key thing here is that I've kind of wrapped it up into an animation using matplotlib, but under the hood, what this animation function is doing is it's making a set of frames calling this function a certain number of times. So the key thing here is this line, where I have the positions of my particles, I have the masses of in my system, I have Newton's constant, and I'm saying I am going to call this function from step 2. That is the thing that evaluates the physics. So I have baked in the physics, and then this is just boilerplate to help me run the simulation. And what you'll be able to do is press play, and it's going to take a little bit of time. You're going to see it says executing. You're going to see it doing a lot of different things on this bar down here. And then once you get the green check mark, and again, this is going to take some time because it's computing. Now it's computing all of those forces on each particle. When you're all done, you should get something that, hopefully, get something that looks like this. And this is our little animation. And what you can do is just press play. Here you'll see there's a play button, and we're doing it. We're off. We're modeling the dynamics of this globular cluster. We're showing what the locations of the particles are in time, what their tracks look like. In other words, what motion did they do? And all we have baked in here is the force of gravity. I've just set up an initial system, and then I said go. I just said use the force of gravity to compute the dynamics. How are we doing on this? Has somebody gotten this? Excellent. So then the fun part now is hopefully our results. Once we've run our simulations, hopefully we get something that approximates the dynamics of a globular cluster. Of course, if I increase the number of particles, I'm going to get something that's more physically realistic. If I do something like decrease my dt, decrease my time step, that's effectively changing the frame rate of my simulation. If I increase my frame rate, which means that I decrease the amount of time between individual frames, that makes for a smoother simulation and also reduces any sort of numerical error. And so what you can do is just play around with different parameters. So, so for this, because you don't have edit privileges to this notebook, it's going to prompt you when you try to change something to save a copy in Drive. So if you have your go.pasadena.edu or you have a Gmail account linked to a Google Drive, that's just going to save a copy in your Google Drive. It's going to be your very own copy, and you're welcome to do with it whatever you want. And so in my case, I'm just going to have some fun. I'm going to change my end time to let it go for longer. I'm going to run the simulation. Okay, so now it's taking longer. It should take 5 times as long, right? We're running it for 5 times as long, but eventually it will produce my product for me. And again, this is just running on one core on some Google server somewhere. So literally one processor on some Google server with a certain amount of random access memory, a certain amount of disk space allocated. And if you had a more powerful computer, so most modern day laptops have something like 4 processors, you can do it that way. And then for these really advanced n-body simulations, like the ones that cosmologically model the behavior of the universe, these are run with like 1 billion particles on the most powerful supercomputers in the world that are exascale, meaning that they have like 10 to the billions and billions of processors. And so you can just run all of these particles. And again, this gets expensive very quickly, but we have the power of modern computing. And this really allows us to model, for example, structure formation in the universe, things like globular cluster dynamics, to allow us to study the physical systems around us. Let me see if mine is finished cooking. Okay, here we go. Let's see what it does. See, I should have decreased my DT to make it a little smoother, but I didn't want things to like completely choke. So just look at this little dynamics. And again, these things are just moving to the force of gravity. So like, you see some trying to escape, and then this cluster is like, no, 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 because we have a lot of mass over here, so you're going to feel the force of gravity going this way, and you can't escape. And that's like one of the reasons that globular clusters, for the most part, stay gravitationally bound. Ooh, look at this, the cluster's drifting. Okay, wonderful. So this is all yours. You can play around with it. You can absolutely, attack the Google servers, making it run like 1,000 particles, for example. I wouldn't recommend more because the scaling is, on something like this, if you're not clever, is pretty bad. But, modern day n-body simulations really have a lot of fascinating techniques in them, like like Barnes-Hut algorithms, stuff like that. But here we just did a toy model. So to kind of summarize where we came from and where we ended up, I tried to stress to us that computation is everywhere in STEM. It's in a lot of fields: aerodynamics, biology, biochemistry, geology, physics, even like something like mathematics. My research field of things like black holes, neutron stars, supernova. If you're interested in that, take my astronomy class. And then we played around ourselves with thinking about some physics, and then thinking about how we can actually use computation to probe an interesting physical system, remembering that doing a computation like this by hand gets really tedious really quickly, because you think about one particle. In this case, maybe there are 100 particles. You have 99 forces to compute for that just one particle, and you have 100 of those guys. So very quickly, it's hard to do this with pencil and paper, and you have to do it for like every time step. So ultimately, we turn to computation to solve this more complicated calculation. Okay, so I hope everyone was able to run the notebook. I mostly got like yes responses from everybody. You're welcome to read more. I linked the code from Philip Mosk that this was kind of based off of. Just to like not reinvent the wheel, but then you can see I made some changes. Again, we used the NumPy and Matplotlib Python libraries. If you're interested in more computation, you can take my physics class. I've changed a lot of the labs to have Python. Or if you're interested in astrophysics, you can take my astronomy class. And that was mainly what I wanted to tell everyone. So hopefully everybody got, a first taste of Python computing and the power of what it can do. This wasn't just a hello world program that we did together. And so thank you everybody for this wonderful opportunity. I do have to run because I'm actually teaching my astronomy class right now. But again, thank you so much everybody, and thank you so much to all the students who made posters. They're truly wonderful, really beautiful. Thank you. Okay, I do have to run. And then if you do have questions for me, you can email me if you like, because I do have to run right now. It's just M and then my last name at pasadena.edu. And it's also on my website. So just Google me and then you'll find it. Okay.
Thank you so much. So we will be taking a break, and then we will start our career and internship panel at 3 o'clock. Thank you guys.
So fun. I want to show you the research posters from my students. They're just right over there, so if you see the individual on the front, they're right behind them. Thank you so much for all your work to get this set up.
No worries.
I'm sorry it was so stress-inducing. I'm so sorry.
Oh, no. Trust me, I do this all the time.
No, I haven't. What is that? Oh, that's awesome. Awesome. Oh, that's fantastic. Yeah. Absolutely. Yes. Thank you so much.